In this video, I'd like to talk about the celebrated Riemann mapping theorem. This is an incredible theorem with lots of applications. So let's get right to this. Okay, so the Riemann mapping theorem. So we were talking about a lot of conformal mappings in different settings. So we discussed Mobius transformations from extended complex plane to itself. And these were mappings that look like that: AZ plus B over CZ plus D with some restrictions on the coefficients A, B, C, D. We also discussed how if you restrict yourself where the C is equal to 0, then you have a linear function AZ plus B, and this is conformal mapping from the complex plane to itself. And infinity maps to infinity. So you could just restrict yourself to look at the plane. Okay, so these are the conformal mappings, angle-preserving maps in this bigger setting. The natural question to ask is, what kind of conformal mappings exist in smaller domains? So the domains that do not take up the entire plane. And this is answered by Riemann mapping theorem. So here's how it's stated. Suppose we have domain D, which is a simply connected domain. So when I say simply connected, I mean it's open, it is connected, and there's no holes inside. But not the whole complex plane. Then there exists a conformal map from that domain to the unit disk. So it really doesn't matter. There's not much restriction to this domain D, just no holes, and it doesn't take up the whole plane. Then that maps to the unit disk. And you can do it in such a way that you have some restrictions. So you could take any point in the original domain, and you could choose to map that into the origin or the center of the unit disk. So that's one restriction you can make. And you don't have quite control over the magnitude of the derivative, but you could choose the argument so that it's a positive number. So if you restrict those two things, then you have a unique conformal map from whatever simply connected domain you had to the unit disk. And this goes even further than that, because conformal map is one-to-one correspondence. If you pick any other simply connected domain, by the same theorem, there's a conformal map from that simply connected domain to the unit disk. Because it's one-to-one correspondence, we have an inverse. And if you compose those two maps, so the first map and the inverse of the second map, you can map from any simply connected domain to any other simply connected domain. So this theorem is actually super flexible. You can get lots of different conformal maps this way. Okay. Actually, let me just state that this is actually a little difficult to prove. Let me tell you what the general outline of the proof would be. So you can show that you can take any simply connected domain and somehow map into the unit disk. So maybe not onto the unit disk, but inside of the unit disk. And then you could do a sequence of approximations. You can make something that's closer and closer towards the full unit disk. So you can maybe the first map is like this, and then you can pick slightly larger and larger maps so it gets closer and closer to the unit disk, and show that the sequence of these conformal mappings has a limit, and the limit is still a conformal map, and it maps to the full disk. That's how it's proved. we don't have enough tools to deal with these type of convergence of conformal maps. So we can show the proof in this class, but it would be a crime for me to not mention this theorem because it is so powerful, beautiful, and important. Okay, so let's look at one type of conformal map like this. So from the upper half plane, let's say the D is the upper half plane, and we're going to map that into the unit disk. The upper half plane is not the whole plane, and it's simply connected, there's no holes. So there should exist some conformal map that does this. How we could do this is actually using the Mobius transformation. Because we know Mobius transformation, we can map this line, which is on the boundary, the real axis, into the circle, unit circle, on the boundary of this disk, in such a way that the upper half plane maps to the inside of that disk. We could do that by picking 3 points on the boundary. So let's say origin, 1, and infinity on this real line. We're going to map that to 1, I, and -1 on the boundary of the unit disk that we want. And kind of imagine walking along this boundary with your left hand inside of the domain and walking along the positive real axis, then that's going to map to 1, I, and -1. So that's how I'm imagining how the map goes. And we know that we can find a Mobius transformation that maps 3 points to 3 other points. So 0, 1, infinity to 1, I, and -1. And this will do what we want. And I know Mobius transformation maps C to C, or the extended complex plane to itself. And it does. The bottom half plane will map to outside of this disk. But we could just ignore that part. We could just restrict ourselves to care about only the upper half plane and map that to inside the disk. Okay, so let's compute it. Let's see. So it's gonna look like AZ plus B over CZ plus D. We're gonna just choose A to be 1. We're just gonna rescale it so that I only have to worry about 3 coefficients. Let's first look at the infinity. So as Z blows up to infinity, this map converges to 1 over C. And we want that to equal to -1, which means C is equal to -1. Okay. So far I have Z plus B is equal to -Z plus D. Okay. Now let's plug in 0. So if I plug in 0 into the function, I get B over D. And we want that to equal to 1. So that means that B is equal to D. Okay. And finally, if I plug in 1, I should get I. So if I plug in 1 plus B over -1 plus B, that should equal I. So we could solve for B here. We can multiply both sides by -1 plus B. So -I plus IB is equal to 1 plus B. Let's get all the B on one side. So IB minus B is equal to 1 plus I. Factor out the B and divide by the coefficient. So B is 1 plus I divided by I minus 1. this could be simplified. Let's just multiply in top and bottom by I plus 1. So let's see, in the numerator, I have I plus 1 minus 1 plus I. And in the denominator, I get 1 squared plus 1. So this simplifies to 2I over 2, or just I. Okay, so my final answer for the Mobius transformation is going to be Z plus I over negative Z plus I. This will map the upper half plane to the unit disk. Okay, so that's a important example. In general, for very funny looking simply connected domains, you could use a software that computes this conformal map to the unit disk. Okay, so I keep saying how powerful this theorem is. Why is this Riemann mapping theorem a big deal? So it turns out that, so it's theoretically important because you can use it to prove a lot of theorems, but putting that aside, it's actually, in science and engineering, it's extremely important because when you have a situation that you wanna understand, let's say in like fluid dynamics, or like you wanna compute how the heat flows within an object. Maybe that object is a very difficult shape. But if you can map it to a very simple shape, like upper half plane or the unit circle, then you could actually do hand computation or solve a problem, difficult problem on that space, and you can kind of map the answer to the difficult domain that you've been working with. So for example, what you could do is like on the flat plane, upper half plane, it's easy to understand how the wind flows. If there's a constant wind blowing from, let's just say west to east, if you map it to a domain that looks like this, where there's like a building built on the ground, the profile of the picture might distort the map in this way. And then you can actually understand the wind flow around the building. So if you had a particular height to the building, you might be able to predict how the wind speed on the ceiling compares to the wind speed on the ground. And this is not a simple computation, but you would be able to do it if you just use the conformal map. Okay. Another thing you might be able to do with so my expertise is in probability theory. And in probability theory, you might work with a random particle. So if there's like a random particle that moves around with no preferred direction, you might care where this particle exits the domain. So there might be certain probability that it exits elsewhere in the domain, but maybe you want to compute what the probability is that it exits in this particular location in the boundary of the domain. This would be super difficult computation to do. But if you solve the same problem on the unit disk, because the particle has no preferred direction, the probability that it exits in a particular arc on the boundary is exactly the length of the arc divided by the 2 pi, which is the circumference. So that probability is extremely easy to compute. You just have to understand how this interval maps to an arc on the unit circle. And this seems like a very weird computation to make, but if you understand how random particles move through an object, then you understand how heat propagates through that object. So if you want to know how the heat spreads on a very weird shape, you just have to understand the heat flow on the unit disk, and then you are able to compute it. You just have to look at the conformal map between the two. So I haven't even begun to scratch the surface of how useful this theorem is, but you might imagine like maybe wind flow around an airplane wing, or these type of computations could be simplified by looking at, you can translate the problem into a very simple shape, upper half plane unit disk, do the computation, and then translate back the problem. This is a very standard approach you could take to a lot of engineering and scientific problems, and you could just do it, and this theorem makes it possible. Okay. I think this is where I want to end the video. I'll see you next week.